Okay, so hello everyone. Um, this video is on introduction to quantum computing, basic things on quantum computing. Of course, the ones who are familiar with the computer are aware of a classical bit, the binary bit which exists in binary state. All of us know binary way of representing numbers. Of course, in short or in a layman language, if I have to say, computer understands anything you give, it's a number or a sentence or anything. Computer understands only one language, that is the language of zeros and ones. All of us know about it. A bit can either be zero or one. Of course, usually zero symbolizes false, and in Boolean way of representing or Boolean algebra, zero is false and one is true. Only this language a computer understands. Now, here I should make a mention that all the computers that we are using now would be called classical computers. Mm, the old ones that we have been using from decades. Now, coming to what is a quantum computer, there's something called a basic unit, of course, bit, quantum bit. So it's called a qubit. Okay, the basic unit of information usually is represented uh, in quantum computer using a qubit. Now, here also we have 0 and 1, but there is a small variation in the representation. Just to distinguish, of course, there are different things associated with it. Slowly you will understand from the next videos what they are all. But you can see this representation. There is one slash and there is one greater than symbol, which is called ket. Usually, all our numbers are enclosed in this notation. And that notation would be called ket. There's nothing new about it. Let me put it like this. All of us are aware of this word bracket. Okay, so anything I write like this would be called ket. Anything I write in enclosed in this braces or whatever, the less than symbol and the slash symbol would be called bra. Just the split of bracket. Okay, yes. First, I will go into the shallow explanation of the mathematical concepts and then probably how things are related to physics or the machine learning things we will see in the upcoming videos. Now, any qubit can be represented in any one or both of the states. Now, what's the difference between a classical bit and a qubit is, now classical bit is like flipping a coin. Flipping a coin. Of course, I can say flip both the cases, qubit or classical bit, in both the cases, we are flipping a coin. But then what exactly we do while flipping a coin is we wait to see how the coin lands, and then once the coin lands on our palm or on the table on which we are expecting the outcome, depending on whether we get a head or a tail, what our expectation is. If our expectation is head and we get a tail, then the output would be considered to be 0 because I have not got a head, instead I got a tail. Similarly, if I get a head and I'm expecting a head and I got a head, then the outcome is expected to be 1 kind of things. Now, coming to a qubit, if you ask me, is it also related to flipping a coin? Yes, it is also related to flipping a coin, but not after the coin has landed. It's like the coin is in the air. I have flipped a coin. The coin is in the air, and then at any point of time when it is flipping in the air, if I want to know in which state it is, if I start interpreting the state in which the coin is at any point of time, then that would be called a qubit. Okay, in a normal coin terminology, where everyone are aware of flipping a coin, those who have come across probability stats or the bits concept of the classical computers. Now, what exactly I mean by saying I want to know the state at certain point of a time when the coin is flipped. Now, what exactly it is suppose if the coin lands, of course, as I have said, it can be either in 0 or in 1. Now, at any point when I am flipping, then the state, if I want to know, then comes the superposition principle. Superposition principle, which would be the combination of ket0 and ket1. Usually I denote it by ket-xi also, ket-xi, which represents the superposition principle of any state when a coin is flipped at any point of time. Okay, though it is confusing, mathematical parts are very interesting provided we are clear with the notation. So first I'll look into the mathematical parts. Now, again, I repeat the second point of the qubit, that is, qubit can be represented in any one of ket0 or ket1 or both of the two states. When I'm talking about both of the two states, then it comes, superposition principle comes into picture. And according to all the people who talk about quantum computing, the superposition principle is the most strongest thing or the most strongest point of quantum computer compared to classical computers. Okay, I'll go into the details a little later in the next videos and all. Now I'll talk about the mathematical notation so that things are easily understandable. When you look at a notation or something, it should not be confusing or it should not scare us. So I'll go into the mathematical notations first and then talk about the physical interpretations. And an element enclosed by the notation, the slash and the greater than symbol, is called state. It's called the state or vector or a ket. Okay. So we call it as a ket, usually ket, of course, sometimes a state also. Now, coming to the superposition principle. Superposition principle is being in both the states, ket0 and ket1. Now, superposition principle, superposition state or something like that, I'll use this ket-xi. Usually, guys, ket-xi is used throughout because there is some relation to this quantum, to the Schrodinger wave equation. Of course, quantum computing is resulting from quantum mechanics. And when I talk about quantum mechanics, it's all about the photoelectric effect of a photon, about which which has been brought into the mathematical way, or which has been brought into the version of computers and all that. The properties of photons or the photoelectric effect, the Heisenberg uncertainty principle, etc. Okay. Ket-xi in superposition principle can be written like this. What that is alpha into ket0 plus beta into ket1. Where, of course, when I'm talking about quantum, I'm not just sticking on to the real numbers. I am extending my concept to complex plane or complex numbers, which is the till date, which is the biggest plane, or all the natural number system or the integer system, the real numbers, the rational, irrational, all are subsets of the complex system or complex plane. Okay, now this alpha and beta need not be just real. I don't constrain or restrict them to be real. Alpha and beta belong to complex plane. Of course, I is understandable. I know if I use I, that means it's an imaginary number. Now the condition is that there's one condition on alpha and beta, with the condition that mod of alpha square plus mod of beta square is equal to 1. Of course, there's a physical interpretation for this as well, which we will talk later. Of course, what is alpha square is mod alpha square tells us the state of mod alpha square tells us the proof to find ket xi in the state ket 0. Mod alpha square is the proof to find ket xi in state 0. Ket xi in state ket 0. There's no number system here. It's all about this ket 0 and ket 1. Of course, I think I should make a mention of what ket 0 and ket 1 are also. Ket 0 is nothing but the vector. It's a vector 1, 0. Ket 1 is the vector 0, 1. The column vector. Of course, you can see that in 2D plane what it represents and all that. Mod alpha square represents it's the proof to find ket alpha in the state ket 0. Of course, mod beta square again is the proof to find ket xi. It's not ket alpha, it is ket xi. Ket xi in state ket 1. Okay. Of course, what is mod alpha square? Because I'm talking about complex numbers, all of us are aware mod alpha square is the resultant of alpha, product of alpha and its conjugate. Similarly, mod beta square is the resultant of beta and its conjugate. Of course, conjugate has a different notation. We can use a bar as well. Bar, conjugate, all of us know. Right. Okay. Now coming to the inner product. There are two things, inner product and outer product, about which I will talk first and then go into the remaining things of the basics of quantum computing or notations of quantum computing. There's one more thing which I will add on and then go to the inner product and outer product. Now, when I am saying ket 0 is 1, 0, guys. There's also another way of writing, as I have made a mention in the beginning of the video. If I write something like this would be called bra 0. Of course, if it is difficult to pronounce, you can also go with this notation, that is dual of ket 0. I can say dual. Okay. Yeah. So what does this represent is my my motive in writing this. Okay. What it represents is very simple. I have written ulta of it, so it's just the transpose. Now, since I know that ket 0 is a vector, it's a transpose. Ket 0 is a column vector, so its transpose would be a row vector. Similarly, when I'm talking about dual of ket 1, that would be represented using this notation, the bra 0, 1. It is this. It's again a row vector, which is 0, 1. Okay. Yeah. With this small information, I go to inner product definition. What exactly inner product is? Of course, as I have shown you something here, it's just being in the state either 0 or 1. When it is classical bit. When it comes to qubit, it can be anywhere when it is flipping. Now, usually people have given the notation that these things are being represented on a Bloch sphere. This spherical representation represents the is the representation for Bloch sphere. Usually all the states are supposed to be represented on this Bloch sphere. Okay. So what exactly are inner product and outer product? Let me tell you. First, the inner product. It measures the relation between two states. How much at what distance they are, at what distance one state is from the other, is what inner product tells us. Those who are aware of mathematical concepts of inner product also, people will know that inner product is just the distance that we will be doing. Okay. So what exactly is inner product? Mathematically, of course, it is denoted using this notation. What exactly is inner product? Let me show with a trivial example in this page and get to another page. If I am talking about inner product of ket 0 and bra 0, how do I write it? Yes. I'll just separate them. There is nothing so to worry about. This is ket 0 and this is bra 0. Okay. What are those? Bra 0 is a row vector. Okay. And then ket 0 is a column vector. So multiplying both, what I'll be getting would be a number resultant of, see here, there's one row and two columns. There are two rows and one column. So obviously the resultant would be a 1 by 1 matrix, or it's just an element. Okay, this is how I will find out. Again, inner product, when I'm finding inner product, these things represent, these have some physical interpretation. Inner product represents the, using inner product, I decide whether the kets are orthogonal, orthonormal, etc. and all. Okay. Similarly, I can go for finding out this one, inner product between 0 and 1, inner product between 1 and 0, inner product between 1 and 1. I'll just show you, which is very easy. Once you understand this notation, many things follow. I've just separated them. Okay, it's bra 0 and ket 1. So bra 0 would be 1 0. And then ket 1 would be 0 1. So the resultant is what? 0. Similarly, this is bra 1 and ket 0. It is nothing but 0 1, the row vector, and 1 0, the column vector. Again, it is 0. Right? Okay. This is bra 1 and ket 1. So 0 1 and 0 1. So the resultant would be 1. Now, what this output symbolizes also has an interpretation, guys. What that is when all of us are aware of orthogonality. Orthogonality, orthonormality. Yeah. Orthogonality is, suppose if two vectors, in terms of vectors, if A bar dot B bar, if this is equal to 0, then I will say both are orthogonal. Why? Simple. The concept is very simple. Usually, angle between two vectors, I'll be measuring using cos theta. What is it? A bar dot B bar by modulus of A bar, modulus of B bar. Right? Now, if they are orthogonal, then theta would be what? 90 degrees. If I put theta is equal to 90 degrees, cos 90 is equal to A bar dot B bar by mod A bar mod B bar. Okay. Now, what is cos 90? As all of us know, it is 0. Hence, I'll be having A bar dot B bar is equal to 0. Okay. So, this is what is orthogonality. Okay. Now, coming to orthonormality between two vectors, guys. It is like this. In a normal layman language, it is like if I have two vectors, if I have a set of vectors, I will say, if I have a set of vectors alpha I, okay, for I is equal to 1 to m or something like that. Okay. Now, if I have alpha I dot alpha j to be 0 for I not equal to j, and to be 1 for, of course, I can put a bar as well because I'm telling that they are vectors, is equal to 1 for I is equal to j, then I will say they are orthonormal. Or in other words, the dot product between two different vectors would be 0. Dot product between the same vectors. Of course, when I'm talking about the dot product between the two vectors where I is equal to j, it's nothing but the distance, right, guys? It is nothing but the distance, right? And the distance is 1. Obviously, I will say that they are orthonormal vectors. Similarly, if you look at this concept, if you look at this same orthonormality concept in terms of the states ket0 and ket1, now I can see that the inner product between two different vectors is 0. Inner product between the same vector or same state is 1. Hence, ket0 and ket1 or orthonormal form orthonormal basis is what I can say. Ket0 and ket1 form orthonormal basis. Okay. So, of course, you can ask me again, if someone who is thorough with linear algebra and mathematical concepts basis, how can you say 0 and 1 form a basis? First of all, if you say, obviously, when I'm telling qubit can be represented either in terms of ket0 or in terms of ket1 or a superposition of ket0 and ket1 when I'm saying, then obviously I can clearly say that ket0 and ket1 form the basis, right? Without that, I cannot write anything in quantum. So they form the basis. Hence, since they form the basis, and then the inner product between them satisfies the criteria, we can say that they form orthonormal basis. Okay, with this I just stop this. I will end this video because it will be too long. We can have some more discussions. I shall share some more information about inner outer products and many things, tensor product, etc. of quantum computing in the coming videos. Thank you.